Now consider a function of two variables, z equals f of xy, for instance. Now, assuming that x and y are both functions of t. So what am I saying? So we have z. Z is a function of x and y. But then x is a function of t and y is a function of t. Oh no. X is a function of t and y is a function of t. Okay? All right. This is usually useful when you want to restrict your domain to a very small subset of the xy plane. What do I mean? So for instance, if we want to restrict our domain to a circle, let's say a circle like that, we want to restrict our domain to this circle. So this circle is x squared plus y squared is equal to maybe say r. But a way of writing the parametric equation of this circle is this, is x is equal to r cosine t and y is equal to r sine t. Okay, where r is the radius. Sorry, this is r squared, not just r. So if we want to consider this function just along this circle, then it will make sense to rewrite the whole function in terms of t, where x is a function of t, r is a constant, so x is a function of t, and y is also a function of t, right? I know you might have questions. You might say, oh, how did we go from x squared plus y squared is equal to r squared to this? Well, this is called parameterization of a curve. We're going to learn about this later on, all right? So I'm just using this to show you an example of where a function of x and y ends up being a function of t, right? Because z is a function of x and y, and then each of x and y are functions of t, right? I'm giving you an example or an instance of where this is useful, all right? So don't worry too much about the r cosine t and r sine t. All right, now, in order to find the derivative of the function f, the best way to go is a tool known as the chain rule. You've looked at the chain rule in R2. This is a version of the chain rule for R3, all right? I'm going to state it as a theorem, which I'm not going to prove because we may not have time for that. So let z be a differentiable function, a function that we can find its derivative. Differentiable function of x and y, okay, on its domain, where, actually, let's use in its domain, well, where x and y are each differentiable functions of t on the interval I. Then on the interval I, the derivative dz dt is equal to the partial derivative of z with respect to x times the derivative of x with respect to t from Calc 1 plus the partial derivative of z with respect to y times the derivative of y with respect to t. And this is this kind of looks like it kind of makes sense, you know. You find the derivative with respect to x and find the derivative with respect to y. You add both of them together, but you might also have the question, why do you have to add them together? All right, it's all in the proof of the theorem, and any calculus textbook should have this proof. So if you look for the proof in your textbook and you have questions, just email me and we can sort it out together if you're interested in reading more about it. So let's look at some examples. Let's look at this problem. Let z be equal to x squared minus 3y squared plus 20, where x is equal to 2 cosine t and y is equal to 2 sine t. All right. So we would like to find dz dt, and we would like to evaluate it at t equals pi over 4. Okay. So this should be easy. Dz dt is equal to partial respect to x times the derivative of x respect to t plus partial respect to y times the derivative of y respect to t. Partial respect to x, take the derivative of z with respect to x, and that means you have to treat y as a constant. So this is just 2x. The derivative of x respect to t is negative 2 sine t plus minus 6y, that's the derivative of z with respect to y, minus 6y times 2 cosine t, right? So this should give us 2x. Let's look at it this way. To give us 4 negative 4x sine t. But you know what? If we want our answer to be just in t, then we have to write x in terms of t, 2 cosine t times minus 2 sine t minus 6 times 2 sine t is 2 cosine t. All right, so this will give you negative 8 cosine t sine t minus 24 sine t cosine t. So this is equal to minus 32 sine t cosine t. All right. So if we, assuming this is our surface, this is the equation of our graph. This is the graph of our equation. What do I mean? Oh, something like this. So assuming this is the graph of the equation, all we're doing is restricting the domain to a circle of radius 2. That's all we're doing. Restrict the domain to a circle of radius 2. Right? Circle of radius 2. So this is the parametric of equation of this is x equals 2 cosine t, y equals 2 sine t. We're going to talk more about this. All right. So let's go back to our theorem. So this says, I'm going to copy this, and I'm going to paste it here. All right. So this is called a tree diagram. This is called a tree diagram. X is a function of t and y is a function of t. If that's the case, this is how you find the derivative with respect to t. Now, how about this? How about if let's extend our theorem a little bit. So instead of uh, having our tree diagram in such a way that Z has the two children X and Y, and the X and Y has just, each of them has one child. But now let's give them two children each. This is S, S, and T. And this one has also S and T. Okay. Then we can find derivative. We can find the derivative. The chain rule says that ds dt now is going to be equal to partial with respect to z times partial with respect to x. Partial of z with respect to x times partial of x with respect to s plus partial of z with respect to y times partial of y with respect to s, right? And then the same thing applies to t. I'm just going to copy. Oh no, I didn't mean to cut. Come on. You should know what's on my mind. I wanted to copy. Copy. All right. Then I paste it here. All right. No. This is what I wanted. I'm going to fix what I wrote. I wanted partial of z with respect to s. Partial of z with respect to s is equal to partial of z with respect to x times dx ds plus dz dy times dy ds. Sorry about that. That's what I meant. Now, I'm going to do the same thing for t, right? So this becomes dz dx times dx dt plus dz dy times dy dt. Okay. All right. Now, let me try another example. 2. Want to let z be equal to sine 2x cosine 3y, where x is equal to s plus t and y is equal to s minus t. And then we would like to find dz, ds, and we would also like to find dz, dt. Okay? Now, so dz dx or dz ds is dz dx then times dx ds, right? So how about we write it? dz dx times dx ds plus dz dy times dy ds. That's all. All right. Let's see. dz dx. Partial respect to x. So we have this. All we have, if we're taking the derivative with respect to x, then this whole thing is a constant. You see that? So we treat it like the constant that it is. Just find the derivative of sine 2x, which gives us 2 cosine 2x times cosine 3y, right? Now, dz, well, we're not done. So this is just, this is just dz dx. Then dx ds. Dx ds is the derivative of x with respect to s. It's just 1 times 1, all right? Okay? Now, dz dy is the derivative with respect to y of z. As far as y is concerned, sine 2x is a constant. So just take the derivative of cosine 3y, all right? Which is minus sine. So we have minus sine 2x, and then times 3 cosine 3y. So we have minus 3 cosine, no, sine 3y. So we have minus and plus here, so we can just change this to minus. And then we have to multiply the result by the derivative of y with respect to s, which is also just 1. It's merciful. Also just 1. So this can be, let's see, 2 cosine 2x cosine 3y minus, why am I rewriting this? Let's try and do something. Let's now substitute s plus t and s minus t in for x and y. So we have 2 cosine 2 x plus t cosine 3 s minus t minus, then we have 3 sine 2 x plus t sine 3 s minus t. All right, so that's our final answer. Now I want you to try this one. Try this yourself. We'll talk about it in class if you're taking the class. All right. Now I want to end this section with implicit differentiation. This is something you're familiar with from Calc 1. Implicit differentiation. Now, I'm going to state a theorem. By now, you already know that I don't prove theorems on the video. I might prove some in class, but not on this video. Let f be differentiable. Let it be a differentiable function on its domain. And we're going to suppose that f of xy is equal to 0. And let's assume this defines y as a differentiable function. Differentiable function of x. Then dy dx is equal to negative fx over fy, provided fy is not equal to 0. Okay, now this is a lot. Let's try to break it down. Let f be a differentiable function. Let's start with a common example. So assuming f is equal to x squared plus y squared, right? Minus 4 is equal to, okay, let f be x squared plus y squared minus 4. And then let's assume that f of x defines y as a differentiable function of x. So if we set f equal to 0, this just implies that x squared plus y squared is equal to 4. So this is a circle. We all know that a circle doesn't pass the vertical line test, so it is not a function. But we can make do with it. We can do something to it to make it a function. So all right, crooked, not crooked, but slant again. No, I want one is straight. Come on, when I want it straight, you gotta give it to me straight. All right. That's weird, but it's okay. All right, so we want a circle like this. All right, this is a circle of radius 2. All right. Now, what I'm saying is that this is not a function of y yet. But if you solve for y, you get plus or minus 4 minus x squared. So if you split it up as plus x squared, or y equals square root of negative square root of 4 minus x squared. So you split up as square root of 4 minus x squared and minus square root of 4 minus x squared. So if you focus just on this one, on this, then you get this part of the circle. And this is a function. This is a function. A semicircle is a function. Now, why am I doing this? I'm trying to explain the theorem. It says, let f be differentiable on its domain, and suppose, so let this f be differentiable on its domain, right? And suppose f of xy is equal to 0. If f of xy being equal to 0 means we get something like this. We get that. Let's assume it defines a differentiable function of x. Now, this green part is a differentiable function of x. This is the x-axis, this is the y-axis, so this is y equals square root of 4 minus x squared. Then, to find dy dx, we just have to find partial of f with respect to x, and then divided by partial of f with respect to y, and throw in a negative sign in front of it. Okay, so let's try this. So that's our example 3. Example 3. We would like to find dy dx if x squared, this is going to be really easy, but I just want to keep it the way it is. If x squared plus y squared minus 4 is equal to 0. And we have to do it 2 methods. One, using the method you studied in Calc 1. So using the implicit differentiation method you studied in Calc 1. Remember the implicit differentiation method you studied in Calc 1? You take the derivative one after the other, but whenever you take a y derivative, you multiply the result by dy dx, and then you solve for dy dx. So this means the derivative of 2x of x squared is 2x, derivative of y squared is 2y dy dx, derivative of negative 4 is 0. So that's minus 0 is equal to 0. Okay? So you solve for dy dx. Dy dx is just going to give you negative 2x all over 2y, which is the same thing as negative x over y. That's our dy dx. All right. Now, I want you to try it using the theorem above. So you want to use negative fx over fy. What is your f? This is your f. This is your f. Copy. Get rid of the 0 here. This is your f of xy is equal to that. All right? It's too close. This is your f of xy. So that means fx is equal to 2x and fy is equal to 2y. that means our dy dx by the theorem is equal to, so dy dx here is equal to negative fx over fy. So that is negative 2. No. Fx is 2x, not 2y. Something is wrong with me. Minus 2x over 2y, which is negative x over y, right? Okay. So I'm going to give you one to try by yourself. Try the two methods. Both the method you use, you know from Calc 1, and this new method. So find dy dx if sine of xy plus pi y squared minus x is equal to 0. Use the two methods. Method 1, implicit differentiation from Calc 1, and then method 2, use the theorem above. Okay, we're gonna stop here. Talk to you.